Hello friends, welcome to the 12th lecture of the Detection and Estimation Theory course. In this lecture, we are going to look at the generalized matched filters. So, in the past lectures, we have looked at the binary hypothesis testing problems in case of wide Gaussian noise. Okay, so we have talked about the binary hypothesis testing in wide Gaussian noise. Okay, so it means that hypothesis H0 is just noise. So this is just noise Wn, and hypothesis H1 is signal plus noise, n0 to capital N minus 1. So in white Gaussian noise, we said that the noise is uncorrelated. So we said that the noise is uncorrelated. That means that the expectation of Wn, Wm for m not equal to n was equal to 0. Now this assumption is hardly valid in practice. In real scenarios, the noise is colored. So the noise is colored in real scenarios, colored noise. What does it mean is that the expectation of Wm, Wn is equal to some value which depends on the difference between the two time stamps. And such kind of a process, a noise process, is called as a wide sense stationary noise process. Okay, what it means is that the mean of noise is again 0, and now the variance is given by a covariance matrix, which is denoted by a C, a capital C, where theCijth element is the expectation of Wi, Wj. Alright, and the noise is again a Gaussian distribution. So I can write this C matrix as something like this. So this is expectation of W0 square. This is expectation of W1 squared, and so on. And the off diagonal elements are expectation of W0, W1, expectation of W0, W2, and so on. This is expectation of W0, W1, expectation of so this will be W0, W2, and so on. Okay, so you can see some of the properties of the C matrix. So it is a first property is that it is a symmetric matrix. Okay, so C is a symmetric matrix that you can see these two elements are same, these are same, and so on. The other property is that it is a positive definite matrix. So this we have discussed in detail in some of the past lectures. It means that for any vector x, x transpose Cx is always greater than 0 for all vector x not equal to 0. Okay, so if you take any non-zero vector x, then this particular entity here is always greater than 0. So because it is a positive definite matrix, the C inverse is also exists. It exists and is also positive definite matrix. Okay, so C inverse also exists and it is a positive definite matrix. Now we want to solve this problem, this detection problem, in case when the noise is colored. Okay, so we are going to solve, we want to solve this problem of hypothesis 0 and hypothesis 1. Again, I'm writing xn is wn, and this is xn is Sn plus Wn, where now noise is a zero mean Gaussian and with a covariance matrix C that is provided to us. Alright, so this is C. Now, how do we detect such kind of a problems? How do we do a detection? We first formulate the likelihood ratio. So here let me write the likelihood ratio. This is equal to the probability of x given H0 hypothesis, H1 hypothesis is correct, divided by the probability of x given H0 hypothesis is correct. Now the probability of x given H1, now this is, as we know, this is a capital N dimensional Gaussian random variable. Okay, x is a n dimensional Gaussian random variable with mean 0. No, sorry, for H1 the mean will be Sn's, and the variance is now given by this covariance matrix here. So this PDF or the likelihood is given by this particular expression. So this is 2 pi power n by 2 determinant of C power half, okay, times exponential of minus half x minus s vector. Now this is a s vector transpose C inverse x minus s. Alright, so this is the likelihood function for x. When the Gaussian is colored, then we write in this particular expression. In a similar fashion, we can write the likelihood of x given hypothesis 0 is correct, which is 2 pi power n by 2 determinant of C power half exponential of, now in this case s is 0, so it becomes half times x transpose C inverse x. Alright, and now let's take the likelihood. Likelihood ratio is we divide the two. When we divide the two, we get as minus half x minus s transpose C inverse x minus s plus, this will go into the numerator, half of x transpose C inverse x. This is greater than lambda to decide hypothesis H1 is correct. Alright, now let's take log on both the sides. So if I take log on both the sides, exponential will go away. So, and I can expand this part here. So let me write it. So this will be, I can also cut half, I can take half to the other side. So let's forget the half part here. So it becomes x transpose C inverse x minus, now the first expression here will be x transpose C inverse x minus, it will be plus x transpose C inverse s. Again it will be a plus S transpose C inverse x, and this is going to be minus S transpose C inverse s is greater than, I'm writing here to be lambda dash. Now you can see these two terms cancel. This is a constant which we can take it to the other side. Now you see these two expressions here. Now what are the dimension of these two expressions? These are scalar quantities. Okay, so these are scalar quantities, and for a scalar quantity A transpose is equal to A. So if I take the transpose of this, it is equivalent to this. So I can write it as twice of X transpose C inverse S is greater than lambda double dash, I can take 2 on the other side and this becomes our final expression. Alright, so this is our test statistics here. So our test statistics is X transpose C inverse of S. Alright, now C inverse is a positive definite matrix. So we can decompose this matrix. So we can write C inverse in a form which we can write it as D transpose D, where D is a non-singular n cross n matrix. Okay, because C inverse is a symmetric and a positive definite matrix, we can decompose it into this format, D transpose D, and D has a special name here, I will tell what. So I can write my Tx to be X transpose D transpose Ts. Alright, so I've replaced this C inverse by this expression here, and let me call this as X dash transpose and let me call it as S dash. So my test statistics becomes X dash transpose D S transpose, where my X dash is X into D. Sorry, D is a matrix, so X into D, and my S is D into, sorry, this is not this, it is D multiplied by X, and this is D multiplied by S. So when you take the transpose, these two interchange. Okay. Now, so I will show you. So D has a special name I was talking about. So D is a special name and it is called as a pre-whitening matrix. Why it is called a pre-whitening matrix? Because see, the noise is colored. The noise is colored always. Okay. So, but when we multiply it with D, when we multiply the noise with D, we get the noise to be white. Okay. So when we multiply the noise with D, it becomes white. I'll show you how. So I'll take this particular expression here. So this is X dash is equal to D times X. Alright. So suppose I am talking about hypothesis 0. So under hypothesis 0, X is just the noise. So it becomes D times W dash. Alright. Now, so this is what? This is my new noise. Okay, so let me call it as W prime. So let me now find out the covariance matrix of this W prime. W prime is going to be again a Gaussian noise, but let me try now find out the covariance. So let me figure out the covariance matrix for this W prime. So how am I going to do is that the covariance of W prime is the expectation of W prime transpose. Alright. So I can write this as expectation of W prime is what? D times W, and W prime transpose will be W transpose D transpose, right? So let me expand this further. So D is a constant, it can come out of the expectation. So this is D times expectation of W transpose D transpose. Now expectation of W transpose is C. So this is D C D transpose, and C I can write it. C inverse we wrote it as D we wrote it as D transpose D, right? So I can write C as D transpose D inverse. So this will be D transpose D inverse, D transpose. Let me open it, so it becomes D inverse, D transpose inverse D transpose, and this is equal to I, the identity matrix. So now you can see the covariance of our new noise when the noise is multiplied by this D matrix becomes identity, which is white. Now the noise, my noise becomes white. That's why our D is called as a pre-whitening matrix. So if I want to draw the replica correlator, so our generalized matched filter looks something like this. We take the input xn, then we multiply it with the matrix D. It is the pre-whitening filter. Then what we do is we multiply it with S dash of n. So S dash of n is generated by, we take Sn and multiply it with D, then multiply it with x of n, then we accumulate the multiplication and then we pass it through a decision maker. If it is greater than gamma dash, it becomes h1. If it is less than gamma dash, it becomes h of 0. So this is the generalized match filter, which is a combination of a replica correlator and a pre-whitening filter. Okay, so in case of a colored noise, we first multiply our signal and our observation by D, and then we follow the normal replica correlator process. Now let's talk about the performance of this particular detector. The performance of this detector, let's talk about it. So for that, my test statistics, as we all know, is X transpose C inverse S. When it is greater than gamma dash, I observe or I detect H1, and if it is less than gamma dash, I detect it to be H0. Okay, so to figure out what is the distribution of Tx, for me to get the PD and PFA, I need to first find out the distribution of T of X. Now to get the distribution of Tx is very simple. See, Tx is under, let's say, hypothesis 0. What will be X transpose? It is just W transpose C inverse of S. Alright. Now you see here, it is what? These two are constants. These are constants. This is a Gaussian n-dimensional Gaussian random variable. Okay. So the overall, it is a Gaussian random variable. Alright. Overall, it is a Gaussian random variable. Now I have to figure out what is the mean and variance of this Gaussian random variable. So let's take the expectation of T of X given hypothesis S0 is correct. See, when I take the expectation of this W transpose C inverse of S, these two are constant, it will come out of the expectation. We will have expectation of W transpose C inverse of S. Expectation of W transpose, we know that it is 0, so this turns out to be 0. Alright. Now what about the variance? Variance of T of X given hypothesis H0 is correct. This is equal to expectation of this square, right? So this square is what? A transpose A. I can write it in that form. Alright. So I can take the transpose. So S transpose C inverse transpose W transpose is W itself times the times W transpose C inverse S. All right. Now you see these two are constants. It will come out of the expectation. So we will have is S transpose C inverse transpose, expectation of W transpose C inverse S. Now we know that this is equal to C. So C and C inverse will cancel out. So this will be equal to S transpose C inverse S. See, C inverse transpose is same because it is a symmetric matrix. Okay. So this is my variance. So my test statistics T of X under hypothesis H0 is distributed as a normal, again a Gaussian, with mean 0, and variance is S transpose C inverse S. Now what remains is to figure out the expectation of T of X under hypothesis H1. So this is equal to the expectation of now my X will be what? S plus W transpose C inverse S. Now let me expand this further. So this is expectation of S transpose C inverse S plus W transpose C inverse S. So the expectation of this is 0, as we saw in the previous case. The expectation is 0. So what remains is only this part, which is S transpose C inverse S. Now you can also do the same exercise with the variance of T of X given H1, and you can see that it turns out to be same as before, which is S transpose C inverse of S. So overall my Tx given H1 is distributed again as a normal with mean S transpose C inverse of S, and variance is also the same as S transpose C inverse of S. So using our earlier concept of how to figure out the probability of detection, which is equal to Q of Q inverse of probability of false alarm minus under root of D square, where D square is the deflection coefficient. So in this case, D square is defined as expectation of Tx given H1 minus expectation of Tx under hypothesis H0 whole square divided by the variance of Tx under any of the hypotheses H1 or H0. So in this case, it turns out that this is equal to S transpose C inverse S. So our PD is equal to Q of Q inverse of P of FA minus under root of S transpose C inverse S. So this is how we evaluate the performance of a particular detector under colored Gaussian noise, and we could see that the analysis was very simple and we could get closed form expressions. So here we end this lecture, and from the next class we will look at the other forms of detector in different scenarios. Specifically, we are going to look at the scenario where the signals are random. We do not know the signals beforehand. Thank you very much.